So while mutual induction covers the same principle, obviously it works on more than one inductor. An inductor is a coil of wire. Mutual, two or more, of course. In this particular case with our ignition coil, we use two inductors or mutual induction. How does it work? Well, on an ignition coil, we have two sets of wires, as you can see here. We also have, that's right, a good old soft iron core. This particular winding, as you can see, it's full of coarse windings. As you can see, the coils are very, very coarse and there's few turns of them. In an ignition system, this is called the primary winding. Very few windings. Ours is called a step-up transformer because we want more voltage to come out of it than we're putting into it. Let's have a look at the secondary. Wow, check that out. Look how many turns there are. See how fine it is? There's heaps and heaps and heaps of windings. Probably in an ignition coil, you're looking at about 20,000 windings in comparison to maybe 200 windings on the primary. And remember, this is called a step-up transformer. We want more voltage to come out of it than we put into it. We put in what? Roughly 12 to 14 volts, and sometimes we can get as high as 90,000 volts out of an ignition coil in today's high energy ignition systems. Remember, as in the case of an alternator with induction, we had to have movement, didn't we? And it was the amount of voltage that we put in, or the current that we put into the rotor, in comparison to the windings that were in the stator, and that multiplied, didn't it? That gave us an output that was higher than what we put in. It was basically like a step-up transformer. So how do we assemble this thing? The primary has to be very close to the secondary. In this case, we put it inside the secondary coil. Don't forget the soft iron core. That fella goes right in there. Let's do some experiments and see what this baby can do. The movement that is required can be mechanical, as in the case of the alternator, where the rotor turns over and that creates an inductive field. In this case, we're going to electrically move the current through there. We're going to switch it off and on. When we turn on our primary or apply power to it, it creates this big magnetic field that builds out and out and out. Then, as we turn it off, just like we saw with our relay, we get the collapsing of the magnetic field, but then there's that inductive kick. We might put in 12 volts, but because of the amount of windings there, we might end up with 300 volts coming out of that inductive kick. And that's just self-induction. Don't forget the mutual induction. Because of the close proximity of the primary winding compared to the secondary winding, remember that magnetic field is being built over the secondary as well, and when that magnetic field collapses, it collapses over the secondary as well, not just the primary, and therefore we get this massive amount of voltage coming out of our secondary. Why? Remember the amount of turns in this secondary winding? I think there was like 20,000 windings, something along those lines. Of course they vary from manufacturer to manufacturer, but remember we've got that 300 volts coming out of our inductive kick from our primary. As the field collapses, it goes over the secondary, and then mutual induction takes place. We get a really high voltage output from this secondary, which of course goes off to our spark plug. Of course, another thing we need to keep in mind is resistance is related to the length of wire, the cross-sectional value, and the type of material that's used. In this case, we're using copper in both. But what's different about the two windings? Remember, the primary has a very, very thick winding, doesn't it? So the electrons can easily get through. There's not much resistance involved, is there? There's few coils on this. So you would expect the resistance to be fairly low, wouldn't you? In actual fact, what's our multimeter saying? Well, what do we got? About 1.1. Now keep in mind that this is only an example of an ignition coil. The amount of windings is only minimal compared to an ignition coil that you would find in your car. Now let's have a look at our secondary. Keep in mind that our secondary has thousands of windings, and they're itty-bitty fellas. The electrons are really going to struggle to get through that, so obviously the resistance will be higher, won't it? Let's just check that out and see what we're reading now. We're reading, what's that, 22.5, something along those lines. You can clearly see that the relationship between resistance in comparison to the thickness of the windings, how thick they are, and how many turns there are in comparison to this one. There's many turns. The cross-sectional value, or how thick this wire is, it's itty-bitty stuff. It's really, really thin. So in this case, we're going to have a higher resistance by comparison to our primary. So I've now got my primary inside the secondary and my soft iron core in there as well, and I'm pumping in some AC signal or AC voltage. Reason is because we need an on-off signal to create this magnetic field that opens and collapses. It expands and collapses, expands and collapses. If we do it with DC, it expands and stays there. So we need some sort of electrical change that will make this magnetic field expand and collapse. So we can see our light is working okay. So I'm just putting in 12 volts, as you can see over here, and yet I'm getting 16.5 volts out here. And my little oscilloscope is showing that we're getting an on-off signal because of AC, of course. It goes like this. You can see it on the power supply right there, the little symbol of AC. So let's just zoom in on that signal there and see what we've got. As you can see, we've got an oscillating sine wave, and that in turn electrically turns the coil off and on, therefore creating mutual induction. Let's see what happens when we do it with DC. You can see the importance of the soft iron core, because if I actually remove it or slowly pull it out, see the light changes. In actual fact, if I remove it, it totally goes out. So that soft iron core is super important for any induction or any electromagnet for that matter. For our DC switching, it's a little more difficult than our AC. Our AC was naturally done by that sine wave of the AC, whereas DC, remember, is kind of a flat voltage that goes across. So I'm going to have to actually create a switching of the DC to make it come off and on. How I've got it set up is I have power from my power supply coming across to my primary, one side of the primary. On the other side of my primary, that goes through a switch back to the negative side of my power supply. On the secondary, I have a load hooked up, so this will be my light here, and I'm going to use my little oscilloscope because it's very difficult to see the switching rate on a multimeter because the sample rate is just too slow. So let's have a look and see what it does. So I've got the power supply turned on, and it's just a matter of switching it, and you can see the coil reacting as well, can't you? So we might just turn that around, I think, like that. You can see the light coming off and on, but what sort of voltage am I getting out of it? Am I getting a transformation? Is it going up in voltage? Remember, we're only putting 12 volts in. Got a really poor signal down here. In actual fact, we're only running about 5.8 volts, which is kind of useless because we're putting in 12 volts. We need something more, don't we? We need to be able to switch it off and on. Now that we're zoomed in on the oscilloscope, we should be able to see a pattern as we turn it off and on. And you can see the effect there. Let's see if we can get a higher voltage out of it than we're putting in. Remember, we're putting in 12 volts, so let's just cycle this fella. Okay, so I've got my oscilloscope hooked up. I've got it as a single shot, so it'll just take a quick snapshot of what we're looking at. Let's see what sort of voltage we can get out of it. Look at that, straight off the screen. You can clearly see that using a switch of some description is super important with DC to get the induction necessary for mutual induction. You can see already it shot off my screen. I can't actually make it any better than that, unfortunately, guys. But just have a look. We're up to 20 volts at the moment. Can you see that written there, 20 volts? Check that out. Can you see what it got up to? 42 volts maximum. That's amazing, isn't it? Simply because of mutual induction. I've only put in 12 volts and I've got 42 volts odd out of it. Pretty amazing. The other day I didn't really wire up my coil correctly, so I thought I'd set the record straight today and show you the difference of the wiring of the coil. We know that we have power going into one side of the primary, don't we? But we also have power going to one side of the secondary as well, which is not what I did the other day. The other side of the primary goes through a switch, as we saw, and then the other side of the secondary goes to our load and then off to earth. So that goes in through series through our load there. But you're saying to yourself, well, hang on a sec, why is the light on? The reason being because of the wiring of the Kettering system. As soon as you turn on your ignition, you have power going to your coil or through to your ignition points, and that's why you can burn out your ignition points if you leave the ignition on for too long. So we don't want to do that, do we? Let's now notice what happens when we switch this beast off and on. So I've gone to my on position. You can see the light just dull a bit. I'm now going to turn the switch off. Wow, did you see that? It was bright, wasn't it? So it's not actually when I turn it on. I'm supplying power to the ignition coil at the moment, but it's when I turn it off. It's that back EMF, isn't it? Keep in mind that my load is actually coming off the secondary, so there's no mechanical connection between the two. It's only relying on back EMF. Let's have a look at the oscilloscope and see what it's doing. I've connected to the output of the secondary, and the other side of my oscilloscope lead is off to ground. Let's have a look. Okay, so I've put the switch on, but it's also just dropped back to zero, really, just a fraction below zero. But I'm going to take my finger off the switch now. Wow, check that out. On, off, on, off, on, off. And of course, when it's going down the road at a rapid rate, it's going to be off and on like that. You can see a little bit of difference in voltage at the top of those peaks. That may be because of the switch itself. Perhaps there's a little bit of arcing going on inside, so there's a bit of variation, very similar to a set of points. Once they start to wear out, you get some uneven voltage peaks. Let's have a closer look at what that is. I've just zoomed in a little bit so you can get a better look at it, but you can see the peak of them is 31 volts. And remember, we're only putting in, I think it's less than 12 at this particular point. The battery's getting a little bit flat. As soon as we turn our switch on, the voltage gets pulled down to ground. As soon as we release it, it gets a massive back EMF coming up here, and that will peak, of course, but then it drops down as the coil drains away. Hopefully this is a little clearer than my tiny little oscilloscope, but the principle remains the same. As we put power on, it's charging up the system, and as we release it, back EMF creates this huge voltage spike, which then in turn goes off to our load. In the case of our ignition system, off to the spark plug. High voltage, low current. I can't keep this up driving down the road, can I? There's got to be a better way to switch DC voltage off and on to get our mutual induction happening in the coil. Yes, there is.